very much. I start to thank the organizer and Gerard, and ask Gerard if I can speak something about Ballas, Egon Ballas. Because it's very important for me, even for Brazil, Argentina, and other countries in that time. Because I studied in France, I worked in France for 5 years, and my advisor was Professor Jean Abadi, who knew Egon Ballas, because I arrived in France 1967, exactly when Egon Ballas got his PhD in mathematics in Paris, in the same university. At that time we call Faculté des Sciences Le Sorbonne. But they changed 3 or 4 times, but don't care the same thing. And in 1976, he went to Brazil because I think he had some cousins, some family in São Paulo. One of his PhD students from Mexico gave him my telephone number. He called me, and we met at that time in Rio, and we started to discuss, and invited him to stay 2 months in Brazil in 1976. He's very nice. He gave a very nice class on disjunctive programming in 1976 in Brazil, and he invited me to give a talk at the International Symposium Mathematical Programming in Budapest. For me, it was my first congress in all the Latin America in that sense. Because when I arrived in Brazil, I returned in 1971, have no fax, no internet. It's not easy to contact the people in European countries or North America. Then we are really isolated in that time. Then, you write and so on, but when he arrived there, he helped me a lot by, sometimes you need, this very common here, ask some recommendation letters, organize things, and accept PhD students, and so on. I remember, even for Sebastian Seria, he called me, who is Sebastian, and so on, from Argentina. It was very important, this connection between us in Brazil and Carnegie Mellon in the United States and France and so on. And he was a really, really interesting guy. And when he spent with us for 2 months, and his wife, Edith, he can read all the languages. In 1 week, he had all the journals paper in Portuguese. He discussed it, because he used to speak a lot. He likes to discuss, he likes political, arts, everything, and have his opinion, very well. Big problem is to go in the car with him when he drives. That's another thing. He bought a car in Brazil. It's so incredible. He's very, very, very happy to drive in Brazil because he's completely crazy, and he's very well in this kind of of the world. That's nice. But I think the more important because is this kind of opportunity we could offer for our students. Have a lot of them who study here. The first postdoctor, my postdoctor, Rui Campelo, I think Gerard know him. I think you knew him between 82, 83. I was at that time a full professor, vice professor at the University of Montreal in Canada for 2 years. And I used to meet at that time Rui Campelo, who was here getting his postdoctor program here with Egon and with you and so on, Gerard. And from that time to few days, a few years. And the last year, in December 2018, he wrote his book. He gave me a book and sent to I have a son living in New Jersey, and my son received the book for me. My friend for the last 42 years, Nelson. It's very nice because we never published together. Work together, organize a lot of things together. He used to go to Brazil, to Argentina. And I think it was very important sometimes to develop the knowledge, the friendship and so on with these people. And he was very important for the optimization, comparative in Brazil, operational search, and applied mathematics. And really important for us. And I think all my colleagues who lived in Brazil, who worked with him and so on, it was very, very nice for us for the kind of open minds for all the things. It's very interesting, all the things. Everything's important for him. Your idea and so on is very, I think is really a very important scholar, and we lose a very important professor, and for me, it's a good friend too. Thank you very much. Then I try to, that's not very important, but it's my job. Okay, do you know, this problem for more than 20 years I tried to solve. That means, of course, when I start to work on the Steiner tree problems, you know, the Euclidean Steiner tree problems, because you have the Steiner tree problems in the graph, on the graph, you see. But this kind is different. They have the n dimensions. I give you p points, and I have to do something else. That's be the idea. You know, Fermat, he used to do a lot of things. Huh? One of his problems, it's one. He give you 3 points and one. Find, okay, the x point, in the sense the summation, the summation of xb plus xc plus xa, the distance, the Euclidean distance will be the minimum possible. The solution will be this kind of things. This means have a point for which the intersection of three, I will see three right there, and in this, all the angles will be 120 degrees. This solution, I don't know, it's supposed to be Torricelli in 1647 who pointed out this point, okay? And when the 3 points of the angles is greater than 120 degrees, of course, the solution will be the given point C. This means you have some kind of degenerate points in the sense, okay? That's Heinen 1937. I read, I'm sure I don't know, okay? That's the first problem. Two kinds of generality of this problem, I think so. For now, suppose P point in n dimensions. And the Weber problem, that you are looking for 1 point for which all the distance will be minimal in the sense. You don't want the Steiner one, okay? And the Steiner one's difference here, just to show the solution, you don't care, huh? That's prefer to things. I think it's much more interesting to see this problem using this kind of example. Suppose we have 4 points, it's 4 square in 2 dimensions. And the first thing we think to find this means I have to connect this 4 point using some cable, something like that. You have to minimize the distance of the total length of this cable. Then the first things you can think you have here at the right, you do that. The length will be equal 3. If you put this point here, it means 2 square of 2. And you have 2 points here, in the sense alpha is 120 degrees, you get this solution, it's the best solution you can do. You have 2 kinds of solution in this case, because this one and this one. Have the topology of what's means, the tree and the distance of the tree. Okay. And then one of the things you know, as I try to show now, find the minimum. That means suppose the P points in n dimension. Look, my talk is associated with n greater or equal 3. For 2 dimensions, you have Joe Steiner. You have another. You don't need to get a model in this sense. Okay. And but I have P points, and I have to in n dimension find a tree that span all these points. Use or not extra points. Extra point we call Steiner points. Why Steiner? Because we never know if it's Steiner or not, but we don't care. Jakob Steiner is from Switzerland. He was professor in Berlin, and it's supposed, I don't know, because we call it Steiner points, but we never know if he's the first one to work on this thing or not. These combinatorial problems, they don't know it's in P hard. You call all the things are Euclidean. Here are some examples. For 3 dimensions, that's on plane. For 3 points, you have just 1 point. For 4 points, like for these 5 points here, you have just 1 Steiner point. For this one, I have 3 Steiner points. For here, you have no Steiner points. Don't need it. Because it's hexagon, all the angles 120. For 6, 7, 8, and so on, so you don't need the one. That's nice. That's mean what you can prove, something like that. Here, just a possible solution of a icosahedron. That's the green point are the verts of icosahedron. The red one that's just a topology, but we don't know I don't know this is the optimal, okay? But it's possible topology in 3 dimensions. That's interesting. It's not difficult to prove. If you have p points, the max of a Steiner point will be p minus 2. That means you have 6 points, given you have 0, 1, 2, and 3, 4, not more. It's the first thing. That's interesting. The second is easy to, you see the valence, the degree of the Steiner point is not degenerate, it's 3. The rating case, the Steiner point is a verse of something else I showed before. Another things, this 120 degrees as you see before, and the Steiner points and the 3 points in the same are in the same plane because you are not in the same place, not the minimal. Okay, that's the idea, some idea. Okay. The number total possibility of topology is things like that. Suppose just for topology with key, that means p equal, as in our dimension, k is p minus 2. Suppose just p equal 10. For 10 points, given point, you have 2,027,000, etc., full topologies. Full, this means with p minus 2 points, just for 10 points. That's the idea is, for each topology, you can find the minimum of this. That's the idea. Suppose you have the 4 points. That's a topology, at least, but not in good position, not yet. You give the position, you have to minimize this fraction here to give the optimal solution here, for this topology. For 4 points in 3 dimensions, you have 4 or more, have 3 different ones, okay? Then for each one, suppose for 10, have 2 million topologies to do that. This is strictly convex, but this it's not differentiable program. But you can solve this problem by alpha and so on. Okay, that's then how to try to have a model for these problems. No? Then I tried, and suppose it's my idea, more than 20 years. I just take 6 points, very easy to draw. I put 6 points, and I know the maximum number of the Steiner point will be 4. I don't know where there, but I know the 4 point will be in the convex hole of the given points, of course, because I minimize this distance, distance Euclidean one. Okay, and then I construct we call this a K4, a complete graph associated with the possible edges, the possible Steiner points. And for each given point, I contact all the supposed Steiner points. Then, if I do that, I got this graph. This graph will be the support or more of my mathematical optimization model, in this sense. Okay, that's the idea, because I know the solution will be, yeah. No. From each given point, I have just one. I have just one edge associated solution. The solution has to be a tree. That means connected graph. That's important. Then I try to associate 2 kinds of a continuous variable that's associated with each Steiner point. I have a vector in n dimension, is variable because they know where it sits, and associated with each edge have a 0, 1 variable. Then I have a 0, 1 variables, and I have to compute the distance between that's mean for each edge. Okay. Then suppose P is index of all the given points, 1, 2 over P. And for P plus 1 over 2P minus 2 will be the index of the variables, X. And we associate with the Xi was the coordinate of the vertex I, P and so on. It's very, okay. And Yij is 0, 1 variable in the sense as you know better than I. 0, you don't need the edge, 1 doesn't need to. Then the first things I try to, the first model I propose at that time, and then we work more. Let's try a look at that. I minimize the distance, Euclidean distance multiplied by Yij. I have to explain you. The first constant, just say, I have just one edge from each given point. Have just one edge associated to this. Of course, if it is not degenerate. And this constant number 3, I will show just to keep this is very nice because the big problem for me how to keep the connectivity of the graphs at the end because I have could have some subgraph, no connect in this case. This is easier than for the I don't need it. I just need this kind of constant. I just show you as I showed the thing. Look at this case because the position of the points can be changed. Okay, you have a click among all the possible Steiner points. I can fix of this. So supposing that 7, 8 equal 1, and look at that. That means all possible solutions in this case are here, just 6. But really, you don't just need 2 of them, because they're isomorphic. You see, this one, and this one are isomorphic. This one and this one are isomorphic. But of course, the total number of possible spanning tree of this 40 is 4 power 2. That means 16. Here I have 6. Okay, in the sense. That means all the solution here will be at least associated with the given points. Then I can guarantee this graph will be connected. Okay. That's to avoid this kind of things. But I think, okay, the first idea I got at that time, there's almost 20 years now. I tried to be separability of the both. Look, I had a product. I knew in that time difference between 2 convex functions to minimize. We can do something better than we could not do. Okay, in this sense, and the constraint number 10 is we know before the solution will be equal 3 for all Steiner points. In this case, you can ask me if the point is degenerate. We don't care, because we can suppose Yij equal 1 and the distance equals 0. Why not? That means the points are together, okay? But the degree of the point will be 3, but this distance will be 0. Then it's okay. Like I can use just all the points, even the solution of 6 points I can find. Okay. This was but because my idea is the relaxation of that. You know, the people who are working in continuous optimization, we can solve these things, of course. Global optimization, you can solve. My idea is that but even to solve, I try to find the Lagrange relaxation, because in this problem I can prove that the optimal solution, the constant number 7 has to be equal 0, but here we can prove it's less or equal 0 because in the optimal solution. Then relaxation will be an interesting problem for me because the relaxation will be even for calculation of the subgradient. All the solution is a convex problem or very easy problem. I don't know. I go direct because I have no time to do that. That means we solve the dual of the problems. Alpha is non-different and so on. All these things you can do that, and you can find the solution because it's a longer way to discuss. But I never use really these things. But I try to do that. And I remember that's some paper about. And with my colleague, Marcel Fampa, we change formulation. We can write exactly like that. That means I replace the minimum, the objective function by Dij. And here, like you see, Dij greater or equal to Dij. Here, AI is the given point because Marcel, she doesn't like to put the same letter for given point and my point. Okay, AI is my xi, and AI is given point, xj is the coordinate, and the Dij. I can replace these problems, and with the big M. The big M will be the large distance between all the given points. Okay, and he's not differentiable. Then I put some lambda square here. This problem now, the relaxation is convex. It's convex. If you put Ij between 0 and 1, continuous 1, this relaxation is convex. Then, okay, perhaps I can try to solve it. And suppose all the things, big M, as I said before, we just explain the idea. And this property is true for P greater than 3. Okay. It's okay. There's more than P, more than 4 points is okay or equal, and so on. And we approach this problem by lambda, but have some error propagation. Look for this problem with the given points. This solution has no Steiner problem. We solve this problem. Look at what's right. If I use lambda square time minus 6, I have a very nice solution. But it's not the better one. Better is this one. I think that's the epsilon as presented by our colleague. Who has worked before here? Gabor, yeah, exactly. Something that's nice because this is very nice problem. We solved with Bonin. Bonin with Leo Libert helped me to solve because all the guidance, the things. But it's nice because you see this difference. But I bet 10 years to find some solution with this model. That's interesting. I have time. 2 minutes. Okay. Just then after that I have some idea. We solve some. The time is very large one. We use Bonin in that time, ample to use and so on to have the idea of the tetrahedral, octahedral cube. I can show his is the easier one. It's the optimal solution. It's octahedral optimal solution. This optimal solution is possible in 3 hours. Now it's much better, but in that time, in 3 hours, we get the optimal solution for the cube. These who don't know, we have the topology, In that time, it was best you could do that. And you have distinct formulation and so on. And here, now, we change the idea. Look, because working with another colleague, we transform this problem, in kind of, you can transform in this way. And then my model can be better than the other one. That means, look at that, let's have it. I have just the objective function is not differentiable, but all the costs are linear with the big M. It is very nice because M can be equal 1. Because you divide everything by M, you have 1. Then for the numerical things. And I try to idea for copy and so on, and my idea how to find a good lower bound. Perhaps change the different way, change just the objective functions. For that, it's very interesting. If I suppose, look, I said before, max might divide by M, and the M will be equal that's the one. Then I can prove for this, in this case, in xik less or equal 1 over n, I can prove that the square is less or equal than the modulus and less or equal than the Euclidean distance. And these problems, this means, I can solve this one, okay, and get this interlinear program, mixed interlinear programming. Then I can find a different bound. And with this bound, we can even perhaps do a Bridgen bound, do something else. Then it's linear, of course, it's linear. It's not linear. We call linear, but it's mixed interlinear programming, okay? But at least we can use simplex, we could do everything, okay? And here m equal 1 disappear, in sense. That m has to be here, the multiplication, the ij, and so on, okay? And here is the square. If you can use, you have another idea to have it, but this bound is not a good one to compare with the one. And you can prove this one. It's nice because you can get new bounds here, and you have the idea. You have this paper. You can see if you want. Okay. Thank you very much. Thank you, Balas. Egon Balas. Yeah. Look, perhaps it's interesting because I could find, of course, you find the topology. And topology is a good one. And then you have to that means I have the topology, the position of the points, not the exactly, that means topology in the sense you have the logical edges, not exactly the points. They have not topology is a good one, but not the position, okay? You have to calculate the position exactly. And you have a very good solution. Some of them are very optimal, okay? We find something, and the bound is very good you compare, but it's not the same problem. That's a big problem. My idea is to solve the Euclidean one. That's okay, it's a good question. But I try to do something, but all the kind of, I try a lot of, what means, relaxation, but I try, and it's nice because if you work between 0 and 1 over n, any dimension, you can have this kind of things. The scale, you change the scale is necessary. You can get something like that. We have nice results now, and perhaps, I don't know. It's open, it's increasing our results, improving.
Any other questions? Well, we have some time in the break, so let's thank Nassim again.
Thank you.